We thought that we would have this talk as sort of a way of mixing together two groups of people, so the periodic and ergodic people and random geometry people. So Kostya promised that his talk would be easily accessible by both groups, and then maybe it would be the start of some discussions. So hopefully we will not just be eating pizza after the talk, we will also have some nice discussions. And Kostya will be talking about, as far as I remember, Hamilton-Jacobi equation and the other KPZ.
Yes.
So the other probably would mean different things for different groups of people. So Kostya will explain which is the proper one and which is the other one.
Yeah. Thank you very much. It's a pleasure to be here. Thank you for inviting me. And actually, it's interesting because the talk was basically announced by, or say, posted by Leonid, but it is a random geometry seminar, so it's all mixed up. And the aim, Leonid told me that they want to kind of try to have some kind of discussion, so interaction between two groups, and they asked me whether I can say something which will be of some interest for both groups, and I hope I will do this. The title is Random Hamilton-Jacobi Equation and the Other KPZ. And the other, it's a very popular word in Cambridge. You know, I mean, in Cambridge, you're not supposed to call Oxford, Oxford. So you say it's the other place. And so if you introduce someone, say he was an undergraduate here in Trinity, then he went to the other place, and then he came back. So this is the notion of other in Cambridge. The title was catered for Nathaniel, I believe, in this program on random geometry, because the main KPZ for this program is Knizhnik-Polyakov-Zamolodchikov KPZ, which appears in quantum gravity and many, basically it's one of the main focuses of the program. And the other one is Kadar-Parisi-Zhang KPZ. And it is very unfortunate that both things are very connected and they come to the same community. And you can have easily conferences where people will be speaking about both KPZ at the same time. So it's kind of misleading. I was for years trying to convince people to use this Knizhnik-Polyakov-Zamolodchikov. I thought it would be something like this will be proper notation, using kind of Greek characters. And then this will be your KPZ, and then there will be that will be Kadar-Parisi-Zhang KPZ, but in vain. Nobody kind of using my notations. Although this is indeed Knizhnik-Polyakov and Zamolodchikov, how it will be written in Russian as well as in Greek. So my plan is the following. I would be kind of motivated by the phenomena of this KPZ, which is extremely universal phenomena which you can basically observe everywhere. And I will explain what it is. It's as general as Gaussian distribution appearing for sums of independent random variables. So basically, if you do certain kind of observational setting, and I've described this setting necessary for KPZ, you always will observe universal behavior. The only difference is that for Gaussian, you can be kind of in any, well, there are no restrictions. Here, you have to be in two decays. So to see KPZ universality, you have to be in two-dimensional space. And so there was a lot of activities about KPZ recently. Well, not recently, in the last, I don't know, 20 years. But still, the problem of universality is very much open. And so KPZ has many aspects. One of them is to get exact formula for predictions of this universal behavior. And there's a big progress in that, because there are certain integrable models where you can get this not very simply looking, but exact formulas. So it's kind of integrable situation, but situation where integrability and universality meet each other. And that is conjectural. There are very few results about universality, as I said. So let me just continue by kind of discussing this phenomenon, this connection between random geometry and KPZ. So basically, you're playing the following game. Imagine that you are in what is called two-dimensional disordered plane. So it means that, for example, you can consider that this is kind of profile of hills and valleys on a plane, some kind of surface, which is order one surface. It's not growing. So it's just something kind of stationary behaved. but random in different places and independently. And then you take two faraway points, and you want to measure distance between them. So find geodesic connecting two points which are far away in this profile. And then you want to ask two questions. You want to see how this optimal path, or geodesic, so it's in a random geometry, so the metric is random here, and they're very far away from each other, and you want to study how much this deviates from the Euclidean geodesic straight line. So what will be the transversal fluctuations of this thing, how far this thing will go. And when the length, which I will denote here n will be the length between them two, Euclidean lengths, so how this scales with n. And this is one question, transversal fluctuations. And second, what will be the length of the thing? So if I denote it Ln, this length, it is kind of clear that it's proportional to n with some coefficient which is normally non-random when n goes to infinity. That's normally you can easily kind of prove because it is ergodic type of behavior, that if Ln divided by n would converge to some non-random constant. But then the next question is, what will the fluctuations? So what are the fluctuations here, and what are the fluctuations here? This is transversal fluctuations. And the predictions of the theory says that doesn't matter what kind of random metric you use, as long as this metric is kind of independent in different places, or weakly dependent even. The size of these fluctuations will be Ln will be of the order of n in power 1/3, and tau n will be of the order of n to the 2/3. And moreover, if I divide these fluctuations on n to the 1/3 or n to the 2/3, the limiting probability distribution will be, they will converge to limiting probability distributions, which also will be universal, will not depend on the details of the random metrics. So that is phenomena, and that is fascinating phenomena. Whatever you do in two-dimensional disordered media, when you want to optimize something in a long distance, giving certain directions. So this is kind of direction is given here. The fluctuations will be well predicted, and they will be of this size. And if I divide by n to the 1/3, n to the 2/3, then, for example, if I take these fluctuations, Ln minus Cn divided by n to the 1/3, well, let me put some number alpha to have to normalize it, but it's just a number to normalize one constant. That will be converging to what is called Tracy-Widom distribution, concrete distribution which appears in the ensembles of random matrices in many aspects. So concrete distribution, not Gaussian, but very concrete. You cannot write formula for the density, but it's a smooth density which behaves very well, decays very fast on one infinity and another infinity. And this is actually, I'm not specifying which Tracy-Widom. There are two Tracy-Widom. There is one for orthogonal ensembles and one for unitary ensembles. And in fact, if you fix n points, then it will be unitary ensemble Tracy-Widoms appearing here. Right, so that's a phenomena. And as I said, there are many activities where people try to get formula for different correlation functions appearing here for different quantities, prediction of probability distribution. For example, what will be the probability distribution of these things? For example, I take it in the middle of this and take fluctuation in the middle point between these two, and then normalize it on n to the 2/3, and again it will converge to predicted probability distribution, which I'm not discussing here. And then the question of what we can say about attempts to find universal behavior here, why universality helps here. Now, this is one of the aspects where this type of KPZ phenomena appears. There are many other settings where you can see such thing, and I maybe mention two of them. So one of them will be the setting which is very popular. Is you are sitting on two-dimensional lattice. That's slightly more convenient for many participants here. So in this two-dimensional lattice, at every point you have a random potential, a random number at every point of this lattice. So take point x belonging to this lattice. At every point there's a random number psi on x. So this is a random field, independent, identically distributed random variables parameterized by Z2. And then that is your potential. That is kind of your random geometry, disordered media. And then the game you play exactly the same. So think about this as a radiation of dust or something. And then you want to go from one point, say from the origin to point NN. And you're allowed to go from along the sides of this lattice. And of course, if you take any path, gamma, which take it from point 0, 0 to NN, so the length of this path will be 2n. You have to make 2n steps, going one up or one to the right, up or to the right. Then for every path, you have action of this path, which is just sum of this random variable psi x when x belongs to the path. And it depends on omega. Omega stands for this random variable. So I fixed, oh, pizza is appearing. So I mean, just finish this piece and then we'll have pizza. So we have this quantity, which is amount of dust you will accumulate when you move from this point to that. You want to minimize it. And then again, the question is, you want to find two things. You want to find gamma 2n bar, which is argmin, the path which will minimize the thing. And you also want to find the action, the amount of dust on this optimal path. And again, you will see the same phenomenon I described here, that this quantity will behave like certain constant, another constant, which is not universal constant, time n, but when you normalize it on n to the 1/3 here, it would converge to Tracy-Widom distribution, the same Tracy-Widom distribution. It doesn't matter what is the distribution of this field, basically conjecturally. But for some examples, it can be proven even. And then the fluctuation of this path, so in my case, it's not a lot of fluctuations, but the fluctuation of this path will be of the order n to the 2/3. And again, we'll have the same limiting distribution if we normalize. So that is a phenomena which I want to deal. And just to finish with this preamble, I would just say that there is another setting where physicists consider this appearing in this phenomena. It's a kind of gross processes. Basically, you consider a long box, and in physics you cannot consider infinitely long box, but it's a very long box which will have length will be much larger than 1. And then at every time, the model is called random depositions. You put some brick here in a random. Every moment of time, you put a brick in a random position. So suppose you have some brick here of size 1, and then maybe here, and so on. And these bricks, they have little wings. So it means that if I put another one on top of it, of course it will go here. But if I put another one on the nearest position, it still sticks here. It cannot go because there is a little wing which doesn't allow it to go through. And then we play this game, putting these bricks more and more. And you can imagine that when you put a lot of bricks, what you will see, it will be a certain interface. And this is interface between things which are covered by bricks. Maybe there are some holes, but everywhere here there are bricks. And then this is empty place. And so you're interested in the properties of this interface. And this interface, that is what is described by what is called KPZ equation, which is actually Hamilton-Jacobi equation, but this particular kind of Hamilton-Jacobi equation, which I'll describe later on. And then if you look at this profile of the thing, it also will show this, after a long time, it will show the fluctuations n to the 1/3 for the height function. So height function has a meaning of this optimal action. So the fluctuation which you see here will be n to the 1/3, and when you normalize on n to the 1/3, so n will be the height, and fluctuation of height will be n to the 1/3, and if you normalize, you will see Tracy-Widom distribution for that. And that's another setting. And in fact, I'm not going into it, but this can be reduced somehow to optimization problem of this type, but I'm not going to do. So it's not so mysterious. But basically, message is whenever you optimize in two-dimensional disordered media on the long distances, you will see KPZ scalings and limiting probability distributions. And of course, it's essential that this kind of Riemannian metric, and if you consider random geometry, which is considered, I believe, in this program, where it's more hyperbolic type of thing, you will not see this phenomena. But for setting I described, you will see this thing. And let me stop here and have pizza. So that's all very nice and interesting, but it's probability somehow. So let's go to a little bit to PDE side, to the other problem. So there is a PDE which describes this type of, which is a very good setting for studying this type of phenomena, and that is what is called Hamilton-Jacobi equation. And this equation will, so let me write it down. So it's phi t plus function h of the gradient of phi. And gradient will always be on a spatial variable. So this will be time derivative, this will be spatial derivative. Let me put here, I would put, say, external force or forcing potential, function dependent on x and t. I put omega here because it will be random very soon, but it's not necessarily, equation doesn't require it to be random, so it's just some scalar function which is a potential of the force acting on the system. This is a Hamiltonian, is a function h on p, which is convex function, smooth convex function, and superlinear in p. And here you can either put nothing, or you can put viscosity, Laplacian of phi, and Laplacian will be in x variable again. V is a positive, nu is a viscosity. You can put zero viscosity, but then it requires certain words to say about it, because this equation has solutions for Cauchy problem, no problem. If you assume that this is smooth function, then its solutions are well defined. What is called strong solutions, they were nice solutions. But in the moment I put viscosity equal to 0, then there are only weak solutions, and there are many weak solutions, but there is a very special weak solution, which is called viscosity solution or entropy solution sometimes, and that is the solution when nu is equal to 0. So basically, definition is the following. One of the definitions, you consider this equation for nu positive, and then take a limit when nu goes to 0, and then special solution appears, and this is called viscosity solution. So I'll be talking only about this viscosity solution. Now, another thing is that example, of course, the classical example will be of the Hamiltonian h on p be equal to p squared over 2, and in this case, this equation is what is called KPZ equation. So when you have here gradient phi square over 2, well, half is not essential. So what is KPZ equation? It's this case, and this is white noise. White noise in x and t. So it's a very irregular forcing. And that is what is called KPZ equation, which supposedly describe this type of phenomena. Now, of course, many of you know about Martin Heirer's work, who considered KPZ equation. His work has nothing to do with the phenomena I'm discussing. So his work was about how to make sense of the solutions to this equation when forcing is that irregular, when it is white in x and t. And the problem is that, of course, it's nonlinear equation, so you have to take square of this object, and this is already square of, that's not a good object. And that's the theory of Martin, is how to regularize it and how to make sense of this solution to this equation. Has nothing to do with what I'm discussing, because it has to do with small scale behavior in x and t, and I'm discussing large scale behavior in x t, so it's completely different phenomena. And for example, I don't want to deal with, I would think that fxt is a smooth function in x. Behavior in t is not so essential, it can be white in t, but in x it is smooth. So I don't have any problems, solution to the equation exists, and they're fine when nu is positive. Okay, so that is kind of disclaimer that what I'm discussing is not connected to what Martin did. And I would insist that I want to consider general H. Not only this case, which corresponds to Burger's equation, to KPZ, and so on. Because basically, the wisdom here is the following, that all these equations have the same properties for Hamiltonians which are convex, at least. Maybe we can go even beyond convexity of this Hamiltonian, but convex properties are the same. Should not be much difference. However, there is a big difference in terms of technique used. And I want to say a word about this. For this particular Hamiltonian, and only for this particular Hamiltonian, you can linearize this equation. there is a notion of Kohl-Hopf transformation. So that if you use Hopf-Hall, then instead of this equation, instead of equation phi t plus 1/2 gradient phi square nu plus f omega xt, you will get linear equation for the function psi, which will be heat equation so f omega xt will be potential multiplied by psi. So it will be heat equation multiplied by the thing. You can reduce to heat equation if you assume that psi is equal to e to the minus 1/2 nu phi. And for this psi, you get this equation. And this equation you can solve, for example, using Feynman-Katz formula. And you can analyze it using Feynman-Katz formula. Feynman-Katz formula would mean that you have to, so what I'm talking about, that you want to consider solution to the Cauchy problem. So you have initial condition, which is function psi x0 at time 0. And then you want to find solution at time t at certain point x. And so you consider Brownian passes going through this point. And then for each of them, you calculate action of this pass. And then you take average with respect of this Brownian pass of the initial condition. And that's how solution can be written. And I'm not going to very much into this direction, but I want to say that that's how directed polymer appears. So directed polymers are exactly this Brownian path going, if you're not prescribing endpoint, they're going everywhere. So it's a Brownian path going there. If you weight them with their action, and action is given by this potential, so you integrate this potential along the path, and then so the action will be e to the minus 1/2 nu, and then you get integral of phi gamma tau d tau. You have to make sense that it does exist because gamma will be Brownian path starting at that point, and then you take average of the thing with initial condition and average with respect of the Brownian path, and that will give you solution to the equation at time t. And so if I consider Brownian path with this Gibbs formula, with this weight, that is directed polymers, which are studied, and I'll say a few words about it. So there is people who are interested in linear theory and linear equations, and most of the people from the program, other program, they are interested in that. That's how kind of Schrödinger type of heat equation appears in this setting, but it will be with time-dependent potential. Most of the activities of the program is not time-dependent potential, but stationary potential. But one can live with it. So that's object which I also will be discussing. However, for general Hamiltonian, you cannot do this thing, and still phenomena will be the same. And so sometimes this directed polymers approach, although very tempting, but I think you're losing intuition and you lose a picture when you make it, because there is a trick here which kind of takes away the physical meaning of what's going on. So I'll discuss it a little bit later. All right. So what is the connection between this type of equations and optimization problem I'm discussing? So the easiest way to discuss it will be for the case of positive viscosity, zero viscosity. So that is what is called Lax-Oleinik variational principle. So I already mentioned that there are special solutions to this equation, which are viscosity solutions. They can be described independently without taking limit. So taking nu positive and taking limit nu going to zero, it's a painful process. Nobody does it. So there is what is called Lax-Oleinik principle, knowing from 50s. And that is how to solve Cauchy problem for that equation. So equation is Hamilton-Jacobi equation. Viscosity is equal to 0. So we're discussing inviscid solution, case where there is no viscosity. And again, there is initial condition here for function phi, which is initial condition in time 0. And I want to find solution phi x at time t. So what you do is the following. So here is time, and here is your space. In this direction, space RD. So dimension can be any dimension. It's not necessarily one dimension. And so you do the following. You consider path, instead of Brownian thing here, you consider just path, smooth path going from this point, from point x at time t, going down in time. So gamma will be from 0 t into Rd, and with the condition that at the end point is equal to x. And you consider all these paths, and there will be absolutely continuous paths, smooth paths. And then for each of these paths, you do the following. You integrate, so you calculate the action of this path. This will be random action. And this will be integral of the Lagrangian corresponding to this Hamiltonian. I will write formula for this at the moment. And here you put gamma dot, velocity of this path. So in Lagrangian, you have to put velocity. In Hamiltonian, you put momentum. And here you put plus f omega gamma tau. Now, remember, it's not a Brownian path. It's a smooth path, so everything here is well defined. You integrate it from 0 to t. And that is the action of the path. Now, Lagrangian is a Legendre transform of the Hamiltonian. So Lagrangian of velocity v is equal to maximum over all v times p minus h on p, or maximum over all p. So that's Lagrangian of the system. If Hamiltonian was a nice convex function, Lagrangian is a nice convex function. In case of Burgers, it will be still v squared over 2. That's how Burgers is special. Lagrangian is the same as Hamiltonian. And that's why you are not distinguishing normally between velocity and momentum. They're the same. But that's unfortunate. So that's an action. And what is the solution about solution? So then you can write formula for solution. Formula solution will be the following. It will be the minimum over all passes gamma with this condition that gamma at t is equal to x. And here you have this action of this path plus initial condition. You also have to add the value of function phi at the initial at this point. So gamma 0, 0. So that's how initial condition come into this thing. And that is solution to the Cauchy problem given by this special solution. So that's, you see what's going on here. Indeed, I want to find optimal path or minimizer for the problem where you have random potential living here. Random potential comes through this function f. It will be just additive here. So, of course, you pay price. Your velocity should not be very large, because otherwise you pay price for that. But the main thing is how to find optimal behavior of this path in this profile. And then if you find this optimal path, then it gives you solution to this equation. All right? And, of course, it's very clear that this is Euler-Lagrange type of functional. And so solution to this equation, gamma necessarily satisfies Euler-Lagrange equation. That's a necessary condition for this gamma. So the equation will be, say, for Burgers, it would be gamma dot is equal to v, v dot is equal to minus gradient of f. So it's a Newton law or Euler-Lagrange equation. So that is solution of Euler-Lagrange equation. So if you know position of this path and you know velocity at this point, then it's uniquely defined. So basically you have to define, just find velocity of this path at that point, and then it's uniquely defined. However, you don't know how to find it. All right, so that's how optimization problem appears in the setting of Hamilton-Jacobi equation for inviscid case. Now, what about viscosity case, when nu is positive? I'll write formula for that. This is also optimization problem, but it's slightly different optimization problem. It's what is called optimal stochastic control problem. And I would write down the thing. So this is kind of counterpart, in a certain sense, of Feynman-Katz formula, in case when you cannot linearize system, that there is no heat equation, there is no Schrödinger equation, so still you can write something which reminds you a little bit of Feynman-Katz formula. You'll see what I will do in a moment, but just one remark is that I will be not interested in solving this equation on short time intervals. I'll be interested in solving this equation on very long time intervals and taking limit when t goes to infinity. So I'll be interested in what's called global solutions to this equation. which valid from OT. And if this is a long time interval, that is a very similar problem. I have to optimize long pass in a disordered two-dimensional media. If dimension d is equal to 1, that will correspond to KPZ. But in fact, this equation can be considered for any dimension. But KPZ will correspond to the equivalent. But the problem is the same. You want to optimize in the disordered media. All right, so what will be formula for nu equal to nu positive? So instead of solution of Euler Lagrange equation, I would consider paths giving by optimal control. So there is one randomness in this problem already. This potential is random. I introduce another randomness, just like I have introduced for directed polymers this Brownian path for which I took just average value. So it's external average. I introduce it for the purpose of writing formula, basically, nothing else. There is no physical meaning for that randomness. So what I'm writing is that suppose I have U, which is optimal control, with some control. U is a function on x and t. And this is assumed to be measurable with respect of, well, you'll see what I will write formula, then it will be clear what I mean. And I would consider gamma U for this control U, which satisfies equation. D gamma is equal U dt plus square root of 2 nu dw. So this is white noise. This is derivative of the Wiener process. So that is external randomness introduced to the problem to write the formula. It's like Wiener processes which I considered before. And this control depends on this omega, on this Wiener process, so it should be measurable so that you can solve this stochastic differential equation. This stochastic differential equation, you can solve it if U is giving. So again, if I take point x at time t, then I'm solving it backward in time. And I get some gamma U if U is giving. It's a curve, again, from 0t into RD. That is random process solution to this equation. Now, if I take this gamma U, I would consider action, which will be similar formula. I would take integral from 0 to t. Instead of gamma dot is not existing here, but U has a meaning of drift term, so it's terms to have meaning of velocity. So I put L on U here, and then I still put integrate phi f omega gamma U tau d tau. So that's analog of this formula, but control U is not determined yet. I add here the value of initial value at gamma U 0, 0. And then I take expectation. Now expectation over my Wiener process. And after this I take infimum over OU. So that is optimal control. It minimizes the thing. So I want to find optimal stochastic control U. And that is a formula for the solution. That is exactly solution to this equation for positive viscosity. So that is analog of the Feynman-Katz formula to a certain extent. Of course, it's much less direct, but it is, has kind of similar meaning, and that will be essential for me. So instead of solution to Euler Lagrange equation, you get solution of this stochastic differential equation. And in fact, you know that it's kind of a little bit implicit, but in fact, you know that in reality, the optimal control U will be in terms of for Burgers, it will be just gradient of this function phi. So if you already know solution of this equation, which is non-random, it doesn't depend on this omega. It doesn't know that. So if you take U, which is a gradient, that's for Burgers. That will be optimal stochastic control. If you plug it here, this is still stochastic equation because of the thing. But in fact, I'm using it in order to find solution. So it's a little bit of the non-implicit description, but still you can still work with it. When I said why it's for Burgers, because for Burgers, velocity and momentum is the same thing. Gradient of phi is p, is momentum. So you have to take conjugate variable, which is velocity. P corresponds to velocity, and that will be u. Anyway, so that's how another optimization problem appears for nu positive, and that is bringing me to a thing which I forgot to say, that this KPZ phenomenon is so universal that it's not necessary even to take minimal curves. You can consider all curves connected to the thing, and weight them with e to their length. So take them with their weight, which will be e to the minus length. So that minimum will be preferred. And even in this case, which corresponds to positive temperature, the behavior will be the same. The scalings will be the same, and the thing will be very similar. Now, what this scalings means, of course, it's not one optimal length, but I'll talk about this later. So basically, universality of KPZ goes for positive temperature and zero temperature. It's a very unusual situation in statistical mechanics where both positive and zero temperature are governed with the same universal behavior, but this is happening here. Maybe I'll say why it is should be expected at least. Okay, so that is a situation. And now let me formulate a conjecture which is proven in some particular cases, but it should be extremely general. So this conjecture says the following, that if I consider this equation either with positive viscosity or with zero viscosity, this is a it's evolutionary equation. I'm solving Cauchy problem for this equation. I'm starting with something and solve it. And of course, if I solve it starting from zero and going up in time, I would not have any limiting behavior, because I'm solving in different environment all the time. I'm moving forward and the environment is changing. This function is changing. And I can have stationary behavior in terms of probability distribution. I can approach stationary probability distribution for solution, but I cannot approach limit. And I'm claiming that you should better do the following thing. It's quite usual in random dynamics. Instead of solving this equation in positive time, you're solving it kind of in negative time. So what you're doing is that you take this equation and you want to construct solution at time zero, but you start with initial condition at time minus t. So this is your solution starting from time minus t with some initial condition. And then you take limit when t goes to infinity. And if you're lucky, if your equations are good, you might hope to have situation that your solution has a limit, because basically it depends on your environment here. Maybe it doesn't depend very much on what's going on below, and this environment stays the same. It doesn't change when t goes to minus infinity. So that situation when limit of this thing exists when t goes to infinity is called 1-4-1 solution. Basically, it means that if you fix your environment, fix your f, there is only one global solution to this equation. And that is special situation. And that will be exactly the situation which we'll have here. So let me just formulate it as a kind of conjecture, and then I say what is known about that.
Before you write, trying to check, so this is this classical Laxalenic, and this is the kind of
positive temperature Laxalenic.
Normalization for positive nu, but then if nu tends to zero, right, this must...
this converges to that. That exactly converges to that. Yeah, that's maybe the best way to derive Laxalenic is to start with this formula and then take a limit when you goes to zero. Exactly, this functional converges to that functional when you goes to zero.
Right. So it's like Laxalenic theory.
This is Laxalenic.
Principle says that this solution is a limited viscosity solution, right? For the
yes.
And
yeah. But it will also give you variational principle. Variational principle is an extremely powerful tool when you have it. Now, let me say that this formula was, the classical citation for the formula is Fleming-Matheson, paper of 1980. It's not a very hard formula. It's rather, if you have written it, it's easy kind of to prove it. I don't know, maybe there are other citations. It's a book of Fleming-Matheson. I don't think it's very well kind of known, this formula. I mean, in some communities it's known. But not universally. And I think it's a powerful and interesting formula. All right. So the conjecture which I want to formulate is the following. That I would formulate it the following way, that in dimension 1 and 2, and also in dimension greater or equal than 3, but I would assume that let me put lambda here. And lambda small. And I don't think it's true for dimension greater than 3 and lambda large, but that's always conjecture. So this is 3. So in dimension 1 and 2, there is no restriction on lambda. And dimension greater or equal to 3, lambda should be small. There is, in both cases, nu equal to 0, nu positive, there's 1/4 one solution. So meaning that this limit exists, I have to say that you have to say something about initial condition. So initial condition, basically let me consider initial condition of the following type. That I would think that phi x at minus t has the following form. It is some linear function plus sublinear function. So you have to fix this b. So if b is fixed, then there exists one solution. So for fixed b, for example, you can take b equal to 0, there exists unique global solution. And just different b's corresponds to different average velocity in the problem, and this is just should not be considered together. Different b's have different solutions, but for fixed b, that is this equation would have one special solution appeared. So another kind of little remark is that, of course, when I say unique solution up to additive constant, because this is potential, it's always defined up to a constant. You can add constant and nothing would change in this equation, but up to additive constant, this is unique solution to this equation. By the way, there is a counterpart for heat equation for what I'm saying. If I write corresponding heat equation, making Hopf call for quadratic Hamiltonian, then the same statement will be correct for the corresponding Schrödinger heat equation, that if you consider heat equations solving from time minus t, they exist unique solution up to multiplicative constant now, because it's e to the phi, unique solution for this equation. Now, so what these dimensions, what all this means? And I would say that in probability theory, the counterpart of this result was known, well, let's say some parts of it were known for some time. And that is what is called first-last passage percolation. So this was studied in the papers by Chuck Newman and co-authors for a long period of time in end of 90s, beginning of 2000s. So setting is the following. There is no equation. And I think it's a weak point of this thing, that there is no equation, so you're losing certain thing. You just live on a lattice, and at every point of lattice there is a random number. That's what I described before, like this dust. And then you want to find path of infinite length, which has minimal property, that you cannot change it on a finite piece and minimize an action gets smaller. That's kind of geodesic. And Chuck proves that in dimension 2, such thing exists. So if you have starting point and direction, and meaning of direction is similar to this b, then there is just one, there's this path of infinite length which is infinite minimizer. So it's very similar to what we need to discuss the thing, because what is behind this kind of conjecture is the fact that the minimization problem we are discussing would have unique minimizer for most of the points. So let me draw the picture which describes what's going on here in terms of the equation, and then I emphasize connection with Chuck Newman and last passage percolation. So, as I said, we're interested in time going to minus infinity, and as well I can assume that I'm looking at time 0, and then I consider some point x, and I want to find path, an infinitely long path. So this path, this is time going this direction, from minus infinity to 0, with the property that whenever I perturb it between any two points, the action can only grow. Because the action which I discussed before It's not a number. It's integral from 0 to t, so it's infinite integral. However, the difference action between white curve and green curve is a well-defined object because it corresponds to integration over this interval, and it's well-defined. So the curve is called minimizer if you cannot take action smaller by doing this thing. Remember that, look at the minimizer doesn't depend on initial condition. Initial condition kind of disappeared. The only remembering is this number b, which is part of the game. But other details of initial condition disappeared. So what you want to prove that for most points, for all points, they exist this optimal path. And for most points, it's unique. And for some points, it's non-unique. And that is an important part of the structure for this equation, and that's what equation tells you, that there are points where such paths still exist, but non-unique, and those special points are called shocks. Those are points of shocks, points of non-uniqueness of minimizers. And they play a very important role in the Hamilton-Jacobi equation if you use interpretation of fluid mechanics or something like that, Burgelens, I'm not going to it. So for most of points it's unique, for some it's non-unique. Now in dimension 1, there is it's geometry of such curves, so it's a hard problem to prove that they exist. And a lot of what Chuck Newman did was to prove existence in discrete setting. Now, in continuous setting, I think it's a more correct problem. It has more structure, and this Hamiltonian structure and Hamilton-Jacobi structure is the essential part of it. There is additional structures which you can use. But there are also some difficulties coming from continuous setting. But what I want to say is that minimizers never intersect. Minimizers don't like to intersect. It's a general fact. Basically, if two minimizers, say, intersect, then you can cut an angle and get something better than that. That's a general property of minimizers. They tend not to intersect. And in dimension 1, this is very serious restriction that they're not intersecting. So basically, there is not much room for them. And what's going on here is that if b is giving, and b is basically the slope of this curve. So in my picture, b is equal to 0, but doesn't matter what is b. When b is giving, there is a bunch of curves going down. And of course, since there is not much room, they would get close to each other. Now, in terms of if you're in a lattice, they would not get close to each other. We'll just come to the same point. So on a lattice, if I would be kind of in a discrete situation, then two minimizers would come to the same point and then go together. But in continuous setting, it cannot happen. That's because these curves are solution to earlier Lagrange equation. They cannot intersect. So what will happen is that two things will come close together, and then they will be exponentially closer and closer together. So they will be asymptotic to each other, but will never meet at the same point. But anyway, what you want to prove is that there exists this kind of tree-like structure of these minimizers, and so many minimizers get together, and so this is a bunch which is going exponentially close together, but they're separated by a shock, so those are also getting together, but there is shock separating them, but maybe sometime later they would come together, and they would meet, and they would start to be exponentially close together, and so on. And so you can prove this picture in certain models. Unfortunately, at the moment, its models are rather degenerate, but it was done in a joint paper with Eric Kator, with Yura Bakhtin, and Eric Kator. Now, this paper has so degenerate forcing that trajectories can get together. So it's very similar to first passage percolation. But there is now a model we're considering where they're not coming together, and I hope we will get similar result of the existence of the conjecture which I formulated in dimension 1. I think we'll be able to prove it in a really continuous setting. Right, now, so what is the picture which you want to discuss? This picture, I think, is essential for the KPZ phenomena, explanation of KPZ phenomena. So let me draw this picture, and that will be kind of geometrical picture. It will be in dimension 1, because dimension 1 plays a special role. Here predictions are mostly known. All right. So I want to describe the picture of the behavior of minimizers and shocks. And there are two dual objects, and that's kind of known in principal statistical mechanics. They're using another terminology. Say in point processes, in interacting particle systems, they consider particles and second-class particles. So second-class particles are basically shocks in their terminology. But here you can see shocks right away. They're points of non-uniqueness, and that is an important object, an unavoidable feature, and that's what makes these equations important in many physical problems. So what is the picture here? And now I would need positive time and negative time. So that's still time equal to 0. So as I said, I would use two different colors. And this color will be for minimizers, will be, say, blue, and red will be for shocks. So as I said, there are these bunches of minimizers which getting exponentially close together, which are separated by some shock points. Another shock point, and so on. Maybe they're getting together here, and so on. But picture the following, that any two minimizer, apparently, after a certain time, will get asymptotic to each other and will start to converge exponentially fast. However, it will take a long time for them to do so. So it will be in a very non-uniform way. Those things start to converge almost right away. Those are separated, and they have to wait until they meet together. Now, what about shocks? Shocks also evolve. So if you have a point of shock for time greater than 0, you still have a shock. So it will be a curve of shock going up. Now, shocks are going up. Minimizers are going down. Shocks are merging. Two shocks can get together, and then they go together. Maybe another shock, and they go together. Now, since they're merging, they're kind of disappearing. But there is a stationary behavior of those shocks. And so what's going on, that some shocks appear. So there are points of appearance of shocks. So it is a point where shock appears. It was no shock before it appears. So what it means is that every shock has an age attached to it. How much in the past this shock can be traced. So this is a point process. And if you look at time 0, all shocks the same. You don't see this age. But in fact, there is an age of each shock. Some of them are old shocks. And the shocks which separate for a long time, they are old shocks, because this shock created somewhere here, and that's how it separates. So basically, if you want to see how long the points, you have to wait until they start to be exponentially convergent to each other. You have to just see how old is the shock between them. The older shock between them, that will be separation between them. So basically, there is this point field of shocks, which is not universal field. And in the moment I will describe almost point field of minimizers. Now this point field of shocks is not universal. So how do I get universal object from here? How do I get universal point field? So I'll do the following. I'll consider here not all the shocks, but only old shocks. So consider shocks which are older than, so age of shock is greater than some large t. So I'm looking only on shocks which created here are not interested, only old shocks. And then it will be much rare set. It will not be a set of density 1, it will be point field with small density. And basically predictions of KPZ means the following, and that's what picture which you want to say, that the density of this set will be 1 over t in power 2/3. The typical distance between two shocks will be t to the 2/3. This is 2/3 appearing in KPZ scaling. So then you normalize it. You consider only those shocks. You normalize it on t to the 2/3, and you get limit point field. We take limit when t goes to infinity and normalize on t to the 2/3. So limiting distribution. So you get limiting distribution of a certain field coming from old shocks. Now, what is the counterpart of it? And that will be the blue points here, point field here. Now, in order to describe this point field, you do the following. You start not at time 0, but you start at time t, which is much greater than 1. And then there are minimizers going from here. It turns out that so from every point there is a minimizer. However, when they cross this line at time 0, they will be very concentrated, because many of them are getting exponentially close to each other. So what you will see, this is not a point. This is exponentially small with t interval of concentration of minimizers, well, it's a difficult picture for me now to draw because there are too many shocks, but there are minimizers coming here, and this is exponentially small interval. And then there is another exponentially small interval, and so on. And so that is the field of concentration of minimizers after a long time. So they'll be concentrated at certain places. They're not just points, but they're exponentially small. So from the view of kind of scaling, they're like points. And again, the density of this, the typical distance will be t to the 2/3. And if you normalize on t to the 2/3, there is a limiting distribution of this field. And this limiting distribution of fields are supposed to be already universal. They would not depend on any of this thing. So the whole of problem of KPZ phenomena is this behavior of these two fields of trio of minimizers and trio of shocks living together, not intersecting, and going up for shocks and going down for minimizers. And the statistics of this, of course, if you don't normalize it, it's not universal, but when you normalize it, it's supposed to be already universal, and that's where the whole thing is hidden. So that's a picture. Very few points of this picture has been proven so far. For some models, there are certain results. Well, let me just tell you one thing, and maybe after that I will be kind of finishing. Actually, two things. I want to explain not how to get tracy Widden, because it's a hard thing and I don't know how to do it. I would explain to you that this strange behavior of the scalings of being t to the 1/3 and t to the being 2/3 can be explained from very innocent behavior of the global solutions which are given by the theorem, or this conjecture which is theorem in certain cases. Okay, so let me just explain this, so it will take away some of the mystery of the KPZ scalings 1/3 and 2/3, and then I would say one more thing. All right. So I would need to formulate another conjecture, again, which is proven in certain very few cases, but no doubt it is a correct conjecture, is the following thing. So there is a limiting solution of this thing, right? Defined up to a constant. So I take this phi x at time 0. This is a global solution. It depends on omega. And let me subtract here phi 0, 0, because it's defined up to a constant. So that's what we're interested in. So conjecture is that this thing has diffusive scaling in x. When x gets enlarged, the difference, the increment of this process, is Gaussian. So in a most naive way, you would just say that if you divide by square root of x and take limit when x goes to infinity, this is a random variable, just a random variable. This converges in distribution to normal distribution. Or you can say even more. If you just rescale it, consider sx 0 minus phi omega 0, 0, and divide it by square root of x, then the alpha square root of x, then it converges to Wiener process, to standard Wiener process on S. Because I want standard, I put alpha here, because I want to destroy the sigma square. So that this is a process with weakly dependent increments. And that's, you can kind of easily imagine that the thing is just, so what is this process phi? It is action of infinite, of optimal paths coming to this point, and that's to that point. And if I take difference between them, they're in different places, they're not strongly dependent. So it's in probability theory, it's kind of the most predicted, the most expected behavior that increments will be not very dependent, and this thing converges to Wiener process. And scaling is, Gaussian is just diffusive scaling. Now, from this conjecture already, the scalings of KPZ follow immediately, n to the 1/3 and t to the 1/3 and 2 to that. So let me show it to you. All right. So I'm trying to explain why this conjecture, which is kind of which takes you away from in PDE, existence and uniqueness result, kind of notorious. People are kind of in other fields saying, oh, it's again the existence uniqueness result. No, it's going beyond that. You say something about statistics of these special solutions. All right? So let me talk a little bit just in the case. Let me assume that we are talking about Burgers or something like that, although it's not essential. So the one piece of structure which I haven't discussed yet is the following. So what we were doing, we were saying that if we consider action of long path, it behaves like constant time t. And constant is non-random. And then there are fluctuations. But I never discussed the properties of this constant. Now I want to say a few words about this constant, which is not universal constant. So I'm looking at the following thing. I start from point of 0, I go until time minus t, so I take a long path. But suppose I allow not all the paths, but I prescribe this point to be on a distance alpha t from the origin. So it will be minus alpha t point. So I consider optimal path which comes to this point. Of course, it's more restrictive, this alpha is giving to you. And there are less paths of this property. So the optimal path, so I take action of the optimal path corresponding to this alpha and divide it by t, and it converges to a limit. This limit c will depend on alpha. This is an average behavior, constant time alpha, what I said before. So if I don't prescribe anything, it would not go far away, it will be near the thing, and it will be the c. But otherwise, c depends on alpha. And of course, the farther I go, the less optimal the thing will be. Now, this is a non-random function, and existence of this function is a very simple fact. It's a subadditive ergodic theorem. That's the only simple fact which you can prove here. It is assumed to be, it's always convex, but it's extremely difficult to prove that it is strictly convex. And so most of models which you can study, it's the models where you can say what this function is, so you have control of this function. And there are ways of doing it, but for particular models, it's actually a shame of statistical mechanics that we cannot prove in general models that it is convex, because it's a random situation, so it's not the general situation will be convex, but it's difficult to prove. Anyway, so this function, I would have the graph. It has some constant when alpha is equal to 0, and then it's some convex function. Suppose you know it's convex. You need it, that this is quadratic minimum. So what it means is that when you prescribe going farther away, you pay price for this, because velocity must be non-zero. And because velocity is non-zero, you here have terms gamma square over 2. You pay price for that. And you can calculate this price. And this is quadratic term which you're paying price. It's just because you have average velocity to come to this point, this term would give you corrections to that thing. Anyway, so this is, let's assume that this is quadratic function. So this function has this type of behavior. Now I'm ready to describe the KPZ scalings. So let me draw the picture. So I would think that I'm in a situation when the global solution exists. Phi omega x t. It's not only on the time 0, but for all t, this global solution exists, and we'll uniquely define up to a additive constant thing. Now, let me take point 0 at time 0 and consider minimizer corresponding to that point. It's a certain curve going down to minus infinity. So what I'm interested in, how far this curve goes at time minus t. So I'm interested in, I'm taking this minimizer and I want to see what is the order of this gamma at minus t, how far it goes at time t. All right? So here there is a function phi x naught living here. Here there is a function phi x minus t. Both functions have the same meaning. This is an action of best path coming to this point, and this is action of best path coming to that point, and so on. So if you went far away from 0, why you are doing that? Because when you're going far away from 0, you pay systematic price for going to this point. According to this formula, if you're going very far away, you pay price. And what will be the price for that? the velocity here will be equal to gamma minus t divided by t. That is velocity. You have to take its square and multiply by t. So that's how much you pay according to, say, Bürger's Lagrangian. So it is order of gamma square minus t divided by t. T is positive. Now, why would you go there, losing this term? Because the value of function at that point, at time minus t, is better than the value at point 0. Just this value is better than that. And you take advantage, because the action of your path will be this number plus the action of this piece. And the action here will be this number plus the action of that piece. Although you're losing here, but you're winning in the value of the thing. But how much you can win? And here is this Gaussian behavior. What you can win, the difference between them has Gaussian behavior if you normalize it on square root of the distance. So this difference is phi minus gamma minus t, and phi 0 minus t. It's of the order of square root of gamma minus t, of the distance. In fact, multiplied by Gaussian quantity. So that's how much you can win. And that's how much you lose for sure. So where you're going when these two things of the same order. Because otherwise you went too little or you went too far. So then your conclusion will be that this should be of the same order. Gamma square minus t divided by t should be of the same order as square root of gamma minus t. So put absolute value, and would give you gamma minus t to be order t to the 2/3. And that's how far you go. Yes, I'm finishing. And that is how far you go. And then fluctuation of the action will be square root of this number because it is just Gaussian. We know it's square root of the distance. So it will be t to the 1/3, which is just square root of that. Square root of t to the 2/3 will be t to the 1/3. So I've just described the pictures which are going on here. So basically, it's very difficult job to work to prove result in this direction. But I believe that attempts to prove universality can be done in this direction. That's where you want to move certain where you want to move. Now, it looks a little bit mysterious for you maybe now when I say that the trajectories get exponentially close. Why would they be trying to get exponentially close? Why this hyperbolic behavior? In fact, it can be explained. And the easiest thing to explain it is for case, not of this case, but case of positive viscosity. Now, you'll say, for positive viscosity, what replaces this optimal path? In fact, you replace it by this kind of polymer measure, which is solution to the equation. So what is analog of polymer measure when Hamiltonian is not quadratic? It's just solution. It is just this. The process. This process is a polymer measure, where u, in fact, is a gradient of phi in case of Bürger's equation. So you can see that this stochastic equation and the law of the thing is kind of analog of polymer measure. And in fact, what you expect to have, that this process will not behave like diffusion process. It will not spread with time, but it will stay with bounded variance. So it will be looking more or less like a curve. It will be kind of spread one. You can explain the thing here in much easier way than for directed polymers, because you know the properties of this vector field, which is velocity field. And so you can understand why the thing would not spread. And that brings me farther away. I don't have time to tell you about this, but there is a lot of structure coming from this stochastic flaws corresponding to this process, or this process itself. And prediction is that these processes will look like a curve. They would have variance order 1. They would go far away, but they're not spreading much with time. And so since they look like curves, they're optimal in similar way, and properties will be very similar. So let me stop here.
So Nathaniel is hinting that there are some...
There's more pizza.
There is more pizza.
You ordered?
Yes.
You should have told me before.
Okay, so should we then postpone questions until? Okay, so let's thank Kosti again.